All right, before we go on with 9-2, I want us to just create like a little cheat sheet because it's holding all back that you don't know your exponents. Okay, so let's go ahead and do some squares. All right, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 64, 9 squared, 10 squared, 11 squared, 12 squared, 13 squared. Well, then I got a little dicey over there. 169. Right, what's 3 times 3? 9, so it's got to end in a 9. 14 squared. Do the multiplication. Well, 4 times 4 is 6, so it ends in a 6. So this is one that ends in a 6. It's going to be slightly 196. That's how I remember them. I don't so much remember exactly what they are. I'm just like, okay, 4 times 4 is going to end in a 6. Oh, that's the 196. Okay. 15 squared. 5 times 5 is going to end in a 5, and it's going to be bigger than 196. 225. Okay, so those, I would know those, no problems. It'd probably even be better to know them to 20, but I'm going to say to 15. 15 should be good. Okay. All right. Let's go back and do a couple of cubes. I don't think you need to know all the cubes, but let's know some important ones. 2 cubed. 8. 3 cubed. 4 cubed. 5 cubed. Good job, Jonathan. 6 cubed. 216. Let's go 7 cubed. Ends in a 3. Okay, I was right. Just double checking. What? Yeah. 343. Okay. I'd say those are the most common ones that you're going to run into. Okay, those are the most common that you're going to run into. Then a couple fourths that you're going to run into. 2 to the 4th. 3 to the 4th. 81. 4 to the 4th. 256. Very good. And just for fun, 5 to the 4th. 25 squared, so 625. And have we done 6 to the 4th? You all did have 6 to the 4th, didn't you all? Was that the 1296? Yep. Okay, so those, it might be helpful to just note, those are ones that come up frequently. Okay, and a couple of fifths. And then we should be good to go. 2 to the 5th. 32, very good. 3 to the 5th. So it's 81 times 3. That's going to be 243. Is that right? Times 3, 3. 8 times 3 is going to be 24. Okay. And then I don't know if we encounter 4 to the 5th or 5 to the 5th often. I'd say if you knew those, you'd be well set. Okay? You at least need to know your squares and your cubes. Okay? And then like basic multiplication would help as well. Okay? All right, any questions about those? You just can't go the long way? Okay. For some reason, 11s give me a trouble, and those are like the easiest ones.
Those are the ones you first taught.
Yeah, like. All right, so that's blurry. All right, let's go on to today's notes, please. Today we are doing 9-2. What was that noise? Somebody just had a cute little noise up here. 9-2, this is exponential and natural log functions. Exponential and natural log functions. All right, the constant E referred to as Euler's constant and Euler is spelled weird. It's not Euler, it's Euler. So the constant E, referred to as Euler's constant, is the base of a natural log function. The constant E, referred to as Euler's constant, is the base of a natural log function. Okay? All right, let's talk about how we're going to go back and forth here. So the first thing I want you to hear is natural log. Log, it's still a logarithm, okay? So here, this is log base E of A equals the natural log of A. Okay, instead of writing log base E, it's used so often in biology, in physics, in math, in finance, that it was just given its own name. ln of A. Logarithm natural. A is this number right here, just like it always is. No, it's not a subscript. Okay? All right, the way that we're going to go back and forth between these is e to the x equals a, right, if that's the base, raised to some exponent, that's going to give us a. That's equivalent to the natural log of a equals x. So just like we went back and forth with normal logarithms and exponentials, we can go back and forth with exponentials and natural logs. It's just that base is always going to be e. Now, Ms. Cleveland, what is e? That's a real good question. Got a video for y'all to watch.
We've made a video about pi, the ratio of a circle's circumference to its diameter. But there's a less famous, but equally fundamental number known to anyone who's taken high school algebra. It's about 2.718281828459045, and so on. And it was first defined by Jacob Bernoulli, but later Leonard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So, if you stick $1 into a bank account with 100% interest rate compounded annually, you'll get $2 at the end of a year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material. So, while E may not be as famous as pi, it's easily as fundamental and immensely important.
Wow.
The number pi.
Now you know. And immensely. Okay. All right. So that's why we should care about E. Let's go ahead and get into some basic properties that you should know. Okay, these are things that were covered in Algebra 1 and Algebra 2, but we're just going to review them just to make sure that we remember them. So basic properties. All right, so the natural log of E equals, pause. All right, so what does natural log mean? What does the symbol ln mean? Log base. Look at your notes. Log base E. So if the base here is E, E to what power gives you E? Okay, E to what power gives you E? 1, right? So anytime you see the natural log of E, that is always equivalent to 1. You can replace it with 1 every time. They are inverse functions of one another. Another basic property, the natural log of e to the x is equal to, okay, let's remember a very basic log property that y'all learned. Anytime you take a log and there's an exponent, remember that this exponent can then come down front. Do y'all remember that? So it can do this. If you're taking the natural log, exponents get to come down in front. Well, what is natural log of e? 1. So this is just equal to x. So there's mathematically how it actually works out. The way I like to think about it is the natural log and e cancel each other out to a 1, and there's nothing to hold the x up, so it falls down. No? No. Okay, natural log and e make a 1, the x falls down. Okay, so that's another basic property. Finally, if we have e to the ln x, e and natural log are inverses of one another, so they're going to cancel one another out, and the x just drops. So there are 3 basic properties that we're going to use over and over and over again. So if I'm doing something weird, chances are I'm using one of these properties. What? Where? Where?
So the E and the L
are inverses of one another. So you know how like when you do like x squared and you take the square root and it cancels out?
Yeah.
Natural log and e have the same relationship as x squared and square root. They cancel one another out. Trinity? equal what is? What does that equal? X. These cancel each other out. Every inverse has its own identity. What is 8 plus a negative 8? 0. So inverses don't always equal 1. They just always have their own particular property. The additive inverse always equals 0. The square root inverse always equals 1, or whatever it is. The multiplicative inverse always equals 1. So there are a lot of different inverses that when you apply them, it equals 1. The arc sine of sine. Okay, so a lot of those we've learned unlock one another. This is just an inverse relationship. Okay, let's get into some examples. I think you'll actually get it a little bit better if we just jump in, just right in there. Okay, here we go. Example 1. We want to simplify. Example 1. Simplify. One of the reasons I like math is because there's a lot of different ways to do it. So I'm going to show you one way. That doesn't mean that's the only way. So if you have an apple plus an apple, how many apples do you have? 2 apples. You have an orange plus an orange, how many oranges do you have? 2 oranges. You do A plus A, how many A's do you have? 2 A's. You do natural log of E plus natural log of E, how many natural logs of E's do you have? 2 natural log of E. So you can combine them just like you can combine anything else in math. But what is the natural log of E? 1 or 2. Now, Ms. Cleveland, why didn't you just say that this one equals 1 and this one equals 1 and 1 plus 1 is 2? Great. Another great way to do this problem. Okay? Right? Like, could have done it either way. I wanted to just show you that you can add them together, you can subtract them, you can do whatever you need to do. What A? Oh, that's just the number. That's just the number that we would plug in. In this case right here, E is the number. A. E is A in this case. You okay? You okay? Let's keep going. I was fine until letters got involved. Right? I was fine in math until letters got involved. Alright, new example. The natural log of e to the 4th plus the natural log of e to the 5th. Now I'm using the second basic property. Right? I could bring the 4 down and multiply it by ln e, and I could bring the 5 down and multiply by ln e. But what's going to happen when I take the natural log of e? They're going to make a 1, so this is just 4. And the natural log of e is going to make a 1, so this is just a 5. This is just 9. Because that really what's happening is that exponent comes down front, and the natural log of e is 1. But we get it. Let's try another one. Actually, let's go ahead and just start solving. Y'all got this. Trust me. Trust me, y'all got it. Solve. Example 3. E to the x is equal to 12. Huh? It's not hard. It's not hard. Now, before, let's think back to really quickly. In the other class, we had like 2 to the x equals 16, right? And we would make this 2 to the x equals 2 to what power gave you 16? 4. So then we would say x equals 4, right? We did that last class. But do we know a way to easily make 12 into a base of e? You do? Okay, I was going to say I don't. So, what I would do here, how would we cancel out an e? A natural log. So here, let's take a natural log of both sides. Now, I've had a lot of kids that are like, multiply both sides by log. Log is not a number, it's an operation. So just like you would take the square root of both sides, or just like you would square both sides, you do something to it, we would take the log of both sides. Okay, so we're applying an operation to it. Well, what is the natural log of e? So all of this is just x. Now let's figure out how to enter this into your calculator. This will be a portion that you're able to use your calculator on. So here's your calculator. Now everybody look on the left-hand side with all of your black keys, and look 2 above the on button. Right next to the 4, you see your LN button. Okay, so then just type in natural log 12, enter. And I get about 2.5. So x is equal to about 2.5. So see, Robin, that wasn't bad. That wasn't bad. That's doable. What'd you say, Katie?
Okay.
Okay, that's not bad. Y'all can do that. Try another one. Okay, example 4. If I'm going too fast, slow me down. 3 times e to the x is equal to 30. 3e to the x equals 30. All right. Well, over here we can apply a natural log because that base was isolated. Since this guy isn't isolated, we can't yet take the natural log. So what should we do first? Divide by 3. You always want to isolate your exponential base or your logarithm before you start applying any of the inverses. So e to the x equals 10. Yeah, to cancel out that x, I'm now going to take the log of both sides, the natural log of both sides. So this is going to cancel, and I just have x is equal to whatever the natural log of 10 is. So go type in natural log 10, and you should get about 2.3. Okay, this isn't terrible. You've got this. This is good. You're getting old.
No, it's not like when I sit down to do my makeup in the morning and my hips start hurting.
Every time I'm standing in front of my sewing machine, like right between my shoulder blades hurt from having to keep good posture, because in America our posture is awful. All right, I think this one's all you. This one's all you. E to the x equals 72. This one's all you. Try it. E to the x equals 72. You should get 4.3 if you did it correctly. To cancel out this e, I need to take the natural log of both sides. The natural log of e to the x is just going to leave me an x. And when you type in natural log of 72, that's where you're going to get about 4.3. Questions on how I got there? Miss Cleveland, just give me that test right now. Just right now. Oh, just over this part? Okay. Okay. Let's switch gears just a little bit. Just as you're getting it. Just as you're getting it, let's switch gears. Number 6. The natural log of 3x is equal to 2. Right, before we were taking the natural log of both sides, but will a natural log do anything to a natural log? No. So here that's not going to work. But what might we be able to do? We are going to apply e to both sides. So here we're going to raise each side by e, So e to the ln of 3x and e squared, right? We're raising each side by e. Totally legal. You can do that as long as you do it to both sides. Now, what's going to happen when I do e to the ln? That's going to cancel, and I'm just left with what on this side? 3x equals e squared, whatever that is, but I'm not going to do it yet because I don't want to round too early in my problem. Now, how would I get x isolated? Divide by 3. So let's talk about how to enter e into our calculator. There are two different ways. Alright, so the first way, if you're ever just needing to multiply by an e, simply go look at your division key. If you type in second division, you just get a little e, and you can just enter it and it goes. That's how, just like you would use it for pi. But if you're actually wanting to raise it to a power, I mean, you can do second division and then add it to a power and whatever. But if you just do second and look on ln, it says, okay, now I know that you're wanting to raise it to a power, and that's the shortest way to actually get there. So I would do e, what is it, squared, e squared divided by 3, and I got about 2.46 or 2.5.
Wait, let me see how you wrote it out. For the actual form, let me see how you wrote it out.
Oh, okay, sorry. Bless you. Okay, so I got e squared because I needed to cancel out this natural log. So I'm going to raise this side as an exponent, and I'm going to raise this side as an exponent. So e to the natural log of 3x and e squared. This cancels, and that 3x falls down, and then I'm left with an e squared over here. Divide both sides by 3. Did you figure it out? That's the operation that you do. That's how you cancel out a natural log. We'll do a couple more because that's weird. You've never just raised it to a power for the heck of it before. Okay. Okay. Question? You got yours answered? Trinity? Weird, but you got it? Okay. Let's try another one. Okay. Example 7. So 2 plus the natural log of x is equal to 10. 2 plus the natural log of x is equal to 10. Now, a couple of moments ago, I told you we had to isolate our bases. You also need to isolate your natural logs. So what am I going to do first? Exactly. I'm going to subtract 2. So the natural log of x is equal to 8. Yeah, how do I cancel out a natural log? Right? E to the power of natural log x is equal to e to the 8th power. X is equal to whatever e to the 8th is. And that's going to be a pretty big number. I'm getting about 2,980.96. I don't like rounding up to the next whole number. It's just me. Because it's misleading. It was 2980 and some change. It was. You didn't earn it. You didn't earn that 4 cents. Okay.
It's not gonna matter in the end.
That's the spirit. Alright, I think this is all you. I think you're ready. Let's take your training wheels off, pumpkins. 3 natural log x equals 9. 3 natural log x equals 9. You've got this.
What is it? 3
I bought an orchid for our classroom today when I went to the grocery store. It's a happy plant. I named it Matilda. You judging me, Leslie? I think she needs a name tag.
She needs a name tag. Named Matilda.
Paid you what? Yet.
show up, right?
You can always assume.
Don't get me mad.
No, I gotta take nothing, I'd say.
Oh, no, you stay on there.
All right. What would you have to do first? I'd have to divide by 3. What you doing over there, Robin?
It was on the floor.
Huh. Huh. With no packaging?
No packing.
E-
Straight off the floor. Probably dirty like that.
You know what? If you that hard up, take it. E cubed, I got about 20.09 or 20.1. Okay, either one. I was being real strict about rounding to 2 decimal places, but then none of y'all did. So I was like, okay, fine. It's not worth the fight. It's not worth the fight. All right. Then the way I'm probably actually going to test this. A word problem. Yay. So exciting. So here we go. When we are doing any type of real world application, you're going to be working with Yabbit. Yabbit.
I'm gonna say that one and then it's gonna have to.
Yabbit. Y equals AE to the BT. Okay. In this equation, Y is always the population after some time has passed. So like after T months or after T years. We'll just put months for this time. I mean, I could do it after seconds. I could do anything that's exponential growth. Y is going to be like your ending population that you're interested in. A is your initial population, or initial amount, there we go. Your initial amount, whatever you're talking about. E is just the constant E that we've been talking about. B is your growth rate. It can also be your decay rate if you're talking about like radioactive materials or if something is decreasing over time. So technically that's your growth or decay rate, but in the problem we're about to do, that's going to be our growth rate. And T was T. Time. Very good. So months, seconds, years, whatever the unit is in the problem. B is growth rate.
B or E?
B. B as in boy. Alright, so the population of bunnies is growing exponentially. Rabbits. Wabbits. At the beginning of the first month, there are 60 bunnies. Okay, so if I tell you that at the beginning there are 60 bunnies, what letter is that? So A is equal to, so this is problem 9. A is equal to 60 bunnies. Okay. And after 6 months, so what would 6 months be? Ooh. T. After 6 months, there are 224 rabbits. What would 224 be? Y. So we want to find B. Problem A is what is your growth rate? Problem A, what is your growth rate? So we need to plug in all of this to our equation and figure out what that is. So let's plug it in. Y, which in this case would be 224, is equal to our initial amount, or 60. E, we don't know what B is, but we know that time was 6. Does everybody see how I got that put into the equation? All right, well, we can't do anything until it's isolated, so what is going to be my first step? Divide by 60. So I have, what is that, about 3.7 equals e to the, and I'm going to rearrange this, 6b, just because that makes my heart happier to have the number first.
Is that 60?
6b. You look like 66. Good one, Miss Cleveland. All right. So now, thank you, Mickey. Now, how would I get this exponent down?
Line, the natural log of
Don't hurt yourself. I need to take the natural log of both sides.
Yeah, that.
Okay? So natural log of this side, natural log of this side. Well, I'm not going to round yet. I'm just going to leave this as natural log 3.7 equals, well, what happens to the natural log of e? Cancels, and we're just left with a 6b. Next step.
Put the E.
Ooh. Divide by 6. So in your calculators, alpha y equals 1. To get a fraction, natural log of 3.7 over 6. If you do this correctly, I've got my growth rate to be about 0.22. Natural log of 3.7,
Over 6.
and then divide that by 6. And you should get about 2.2. 2.216 or something.
0.21.
What did I say?
You said 2.6.
You right. 0.216 or 0.22.
Mine said 0.21.
Okay.
Same thing. Same thing.
Whoa, 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 whoa. Okay. So then it'll say, like, write a model to describe this situation. All that means is now that you have b, write your general equation, leaving y and t alone. So y equals my initial amount, which was 60, e, now I know b to be 0.22 t. If I ask you to write a model, all I'm asking you to do is write the equation with the growth rate in it. Okay? Huh? When I'm asking for a model, it could be any time or any population. So we're just asking for the general equation. So just leave y and t alone. Okay? The final thing I could ask is, like, I could give you a scenario. So how many months before there are 600 bunnies? Bless you. How many months before there are 600 bunnies? Okay, well, what would 600 be? That would be y, right? That would be your ending population that we're interested in. So we're going to plug that in, and now we're having to solve for how many months, or t. So 600 is equal to 60 e to the 0.22 t. Let's go ahead and start solving this. What would I do first? Excellent. Divide by 60. So that is 10. Is equal to e to the 0.22 t. Right? What am I going to do to cancel that e? I'm going to take the natural log of both sides. So the natural log of 10 is equal to 0.22 t. Final step. Divide by 0.22. Enter that into your calculator. Make sure you can do it correctly. I'm getting about 10.5 months. Okay, you should get in the neighborhood of 10.5. Okay, good.
10.5.
It is. All right. Homework is on Canvas on your own paper again. That didn't work out so well last time, so may you do better this time. Okay? All right. If you need help, come see me. Remember, all tests, if you were absent, need to be made up by Monday.
I just want to know what I made on my